Building a deep space probe is a complex task. Today we build them on Earth. They must be strong enough to survive a rocket launch. They must be small enough to fit inside a rocket's nose cone. This limits their size and shape. But imagine a different way. Imagine we built these probes in space. An orbital shipyard, a factory floating above Earth, could change everything. This change in location could let us build bigger, more capable machines, enabling larger instruments for deep space exploration. This essay will explain how orbital shipyards could work. We'll look at the specific steps involved. We'll use simple terms to describe the process. The focus is on what's possible with today's technology. We won't use science fiction ideas. The goal is to show how this method could reshape space exploration. It is slow and methodical, not a sudden revolution. It involves many challenges and careful planning. We'll explore real-world limits. Building in space is expensive. It's difficult. We need to understand the costs. We must look at potential delays and failures. Every new step introduces new risks to manage. We'll examine who would have interest. Space agencies, private companies, scientists. Their goals and incentives will shape development. Finally, we'll consider long-term effects. If orbital building becomes common, how would probes change? What new missions could we attempt? It could create a new state of space activity with complex structures assembled far from Earth. An orbital shipyard is a construction site in space. It is a permanent or semi-permanent structure. It would orbit the Earth, likely in a low orbit. This makes it easier to reach with rockets from the ground. The shipyard would be a place where large components are brought together. Robots, and, in some cases, human astronauts would assemble them. The final product would be a complete spacecraft, ready for its journey into deep space. It is a factory, but its environment is the vacuum of space. The shipyard would need essential systems to function. It needs a source of power, most likely from large solar panels. It would have robotic arms for moving and joining large parts. It needs docking ports where cargo spacecraft can deliver new components and supplies. It also requires storage areas to hold these parts until they are needed for assembly. The entire facility would be designed for building things in microgravity, where objects are weightless. This is very different from a factory on Earth. One of the key features of an orbital shipyard is its ability to handle large structures. The main reason to build in orbit is to escape the tyranny of the rocket fairing. A rocket fairing is the nose cone that covers the payload. It has a fixed size. Every probe launched from Earth must be designed to fold up and fit inside it. This constraint has shaped every deep space mission ever flown. Engineers spend a great deal of time and effort making complex structures that can unfold in space. This adds weight, complexity, and potential points of failure. Building in orbit removes this size constraint completely. A probe's components can be launched in many different rockets. The pieces can be large and simple. Small and complex parts are no longer required. Imagine a telescope with a mirror far larger than any single rocket could carry. It could be launched in segments, then assembled in orbit. Designs can be optimized for their mission, not for Earth launch. The result, more powerful instruments for science and exploration. Launch strategy changes. Instead of one very large, expensive rocket, you could use several smaller, cheaper launches. Like moving furniture into a house piece by piece. That makes missions more resilient. If one launch fails, only part is lost. The rest can still fly, and replacements can be sent. Building in orbit also allows for final checks and refueling before departure. Once launched from Earth, a probe is already on its way. You can't fix problems or add fuel then. At an orbital shipyard, the completed probe can be fully tested in space, systems checked and rechecked, fuel tankers can dock and fill tanks for a long journey. This final preparation greatly increases mission success. So what are some of the hurdles on the high frontier? Costs, delays, limits. The biggest hurdle for orbital shipyards is cost. Sending anything to orbit is expensive. Every kilogram of material, every tool, every spare part must be launched on a rocket. The cost of building and maintaining the shipyard itself would be enormous. It would require many launches just to get the basic factory into orbit. For this idea to be practical, the total cost of a mission built in orbit must be less than the cost of a traditional mission launched from Earth. This is a very high threshold to cross. Delays are another significant problem. Building in orbit adds many extra steps to a mission. Each component must be manufactured on Earth, launched into space, and then transported to the shipyard. A delay in any one of these steps can cause a cascade of delays for the entire project. If a rocket launch is postponed due to weather, the assembly process in orbit must wait. These delays add to the overall cost and complexity of the mission. There are also technical limits to consider. Working in space is hard. Robots need to be extremely reliable. If a critical assembly robot breaks down, the entire shipyard could be put on hold. The space environment is harsh. Extreme temperatures, radiation that can damage electronics and materials. The shipyard must be designed to withstand these conditions for many years. So, who builds and who pays? The key players. The primary players pushing for orbital shipyards would be national space agencies. Groups like NASA or the European Space Agency are focused on large-scale science missions. They want to send bigger and more capable probes to the outer planets, asteroids beyond. An orbital shipyard would enable missions that are currently impossible due to size limits. These agencies have the large budgets and long-term vision needed to fund the initial development of such a massive project. They see it as an investment in future exploration capabilities. Private aerospace companies would also play a crucial role. They would be the ones to design and build the shipyard itself. They would also operate the launch vehicles that carry components and supplies from Earth. For these companies, an orbital shipyard represents a new market. They could sell construction services to space agencies, other companies, wealthy nations. Their incentive is profit. They would only invest if they believe there is a sustainable business case for building things in orbit. Scientists and research institutions are another key group. They are the end users of the data that deep space probes collect. They would advocate for orbital shipyards because it would allow them to design more ambitious experiments. A larger telescope could see farther into the universe. A bigger lander could carry more instruments to the surface of a moon. The scientific community would provide the justification for these expensive missions by highlighting the new knowledge they could unlock. Their demand for better data drives the need for bigger probes. To make this happen, laws and financial models must change. International agreements would be needed to govern the use of an orbital shipyard. Rules for liability in case of an accident would have to be established. Financially, new models of public-private partnerships would be required. A government agency might pay for the initial construction. Private companies would compete to offer launch and assembly services at a fixed price. This would spread the risk and encourage efficiency. Now, we move to assembling a probe in orbit. A step-by-step example. Let us consider a clear example. Building a large probe to map the ice on Jupiter's moon, Europa. The probe needs a huge radar antenna to see through the thick ice. This antenna is too big to fit in any existing rocket. The first step is to design the probe in a modular way. The antenna, the main body, the power system, the propulsion system, are all designed as separate pieces. These pieces are then built on Earth. The second step is launching the components. A series of rocket launches would carry the pieces into low Earth orbit. Each launch would deliver 1 or 2 modules to the orbital shipyard. This might take several months, as each launch is scheduled and prepared. They would start by building the main truss of the spacecraft. Then, they would attach the large antenna panels one by one, carefully connecting them to form a massive dish. After the antenna, they would attach the main body with all its scientific instruments. Finally, the power and propulsion modules are connected. Human astronauts might supervise or assist with complex wiring tasks. The final step is testing and deployment. Once assembled, the probe is not yet ready to go. It undergoes a full systems check in the vacuum of space. Engineers on Earth remotely test every instrument, computer, and thruster. A separate refueling spacecraft would then arrive and fill the probe's tanks with fuel. After a final check, the probe is released from the shipyard. It fires its engines and begins its long, multi-year journey to Jupiter. A failure at any of these steps, such as a launch failure, an assembly robot malfunction, long-term futures, a new era of exploration. If orbital shipyards become a reality, they will fundamentally change how we design spacecraft. Engineers would no longer be constrained by the size of a rocket. They could think bigger. Probes would become more modular, designed for assembly in space, rather than for survival during launch. This could lead to a new generation of deep space missions. We could see massive space telescopes, large interplanetary transport vehicles, or complex multi-part missions to the outer planets. The focus would shift from compact design to mission performance. The existence of orbital shipyards would create a new layer in the space economy. A whole industry could develop around in-orbit services. Manufacturing, assembly, refueling, repair. Low Earth orbit would transform from a destination into a bustling industrial zone. Launch providers would shift their business model. Instead of launching one-of-a-kind expensive satellites, they would focus on standardized, frequent cargo deliveries to orbit. This would create a more robust and interconnected system of space logistics. This new state of affairs would be stable if two conditions are met. First, the cost of launching mass to orbit must continue to fall and remain low. Second, the rate of failures in orbit must be kept very low. If launches become expensive again, or if assembly in space proves too risky and unreliable, the system would not be sustainable. The industry would likely revert to the old model of building everything on Earth. The success of this new era depends entirely on cost-effectiveness and reliability. This shift from Earth-based to orbit-based construction represents a major step in our expansion into space. It is not about a single breakthrough technology. It is about changing a process. It moves the factory from the ground to the sky. This change trades the known limits of rockets for the new challenges of orbital logistics. The path is incremental, built on lowering costs and improving robotic capabilities over decades. The ultimate outcome is not guaranteed, but the potential is significant. If we can master building in space, how will our view of the solar system change when we can build probes as large as we can imagine? What scenario should we explore next? Share your ideas below. You've been watching IfVerse, where imagination meets possibility. See you in our next reality.